Hey, hello everyone. Welcome back to the videos, and in this video, we're gonna talk about the Taylor polynomials. And for short, I would say that the Taylor polynomial is just the function approximation, but is a little bit better than the linear approximation that you have already learned in calculus one. So if you still remembers in calculus one, after you learn about derivative and some of the question ask you to write down the tangent line. Okay, so that means let me suppose that this is the curve of the function. Okay, and the question want you to write down the tangent line to the function at the points a f of a. Okay, that belong to the curve. Okay, so you place the tangent line, and this tangent line is, I would say that this is the tangent line formulation. Okay, this is the tangent line formulation, and you can pretty much see that. I mean, f of a is a number. F prime of a is the number as well. So technically, the thing you have for the linear approximation is the polynomial of degree one. Okay, the polynomial of degree one. Polynomial of degree one. Sorry, degree one. Okay, because you see that you just have x to the power of one. Okay, and the thing is, I mean, the reason is why do we need the function approximation? So for instance, like if you have some arbitrary function, like let me suppose that you have y equal to psi of x, right? And like if there is some if there's somebody asks you like what is the output of the function, uh what is the output of the function at x equal to 0, then you can just simply plug in 0. You have psi of 0 equal to 0. Okay, but what if the there is somebody ask that what is the output of the function at x equal to zero point 0.1, then you have to find psi of 0.1, right? The reason is it's not easy to find psi of 0.1, but the point is with the help of the function approximation, and most of the time you're gonna approximate the function by the polynomial. Okay, so the point is, for instance, let me suppose this is the point that you want to find. Okay, so from here you see that the point is that if you can write down the tangent line equation, if you can write down the tangent line equation at x equal to 0, then you can use that approximation to kind of approximate the output of your function at the point one. Okay, because you see that uh, at, in the neighborhood of the locations, in the neighborhood of the locations where you place the tangent line, the output of the green curve and the output of the red curve is quite similar. You see that there's no big difference between the output of the green curve and the output of the red curve around this point. Around this point, the output is quite similar. So that means if you want to compute the output of the green curve around the point that you place the tangent line, then you can use the output of the red line as the approximation. So that's why um, you need the function approximation. I mean, there is just uh, uh, one of the applications of the function approximation. Uh, there is a bunch of application, but you may see it better if you learn advanced analysis or advanced calculus. But so far, I just want to I mean, in this video, I just want to mention that there is a way. I mean, for any type of function, there is a way to approximate them, to approximate the output of them. Okay, and we're gonna approximate the function. by the polynomial. Okay, and we call them Taylor polynomials. So, and the thing you learn in calculus one, which is the linear approximation, is also type of Taylor polynomial. But the thing is, you just use the linear function, which is a function, which is the polynomial of degree one. Okay, and in calculus two, you're gonna do something a little bit better. Okay, you're gonna use a lot of information. Okay, I mean you will use the order two polynomial, okay, or the order three polynomial to approximate your function. That means that is a little bit better than that is much better than the linear approximation that you learn in calculus one. Okay, so let me let me discuss several things before we we move on the in general formulations of the Taylor polynomial. Okay, so over here, after I read out the tangent line equation, okay, after I finished my tangent line equation, I denote this thing as t sub one x. So t sub one x indicate that this is the Taylor polynomial of degree one. Okay, and Taylor polynomial of degrees one. Okay, I mean T1 of x is called the first degree Taylor polynomial. And the good thing about this approximation is, okay, the good thing about this Taylor polynomial is it's a the first degree. This is a degree one polynomial that have the same output with the original function, and the slope of your polynomial is also the same as the slope of your function at the point A. Okay, T1x is the first degree Taylor polynomial of f of x about the point A if it has the linear form, which is the first degree polynomial. You see that x is power of one, and more than that, this polynomial have the same output with the function f at A, and it also carried the information about the slope field of the function at A. Okay, so that means it kind of mimic the behaviors of the function. Okay, it kind of mimic the behaviors of the function around the points A and f of A. Okay, you see that the function is increasing, and the red line is also kind of increasing in that neighborhood as well. Okay, so the Taylor polynomial the degree one Taylor polynomial will carry two information: the output of the function at that point A, and it also carry the information about the rate of change of the original function at the point A as well. And for the now let I mean this is a thing you already learned in calculus one. We just use a different name for the linear approximation. We call it the degree one Taylor polynomial. So what is the second order approximation to the function f at the same point A? Okay. So when we talk about the second order approximation, that means the polynomials of approximation. The polynomial that we're gonna use will have degree two. So you can see that you have one more extra terms. Okay, you have one more extra terms, and the thing is, for the second order approximation, it has to carry some information. I mean, the, the for the approximation, for instance, over here, the first degree Taylor polynomial, they carry two information: the output of the function at A, the slope field of the function, and the slope of the function at the points A as well. So for the second order approximation, it will carry more it should carry more information compared to the first degree approximation. For the second order approximation, again, it will your approximation, the function will have firstly the approximation will be the polynomial of degree two. The second thing is it will carry the information of the original function at A. So the output of the polynomial and the output of the function f will be the same at the point A. The polynomial with the polynomial approximation that you consider also carry the informations about the slope field. Okay, and more than that, the approximated polynomial that you use also carry the concavities of the original function. That means b p double primes of a equal to f double primes of a. So for the second order approximation, it will carry three important information: the output of the function, the output of the original function. Your approximation should carry the slope of the original function, and the approximation polynomial should carry the information about the concavities of the original function. So that is what is second order approximations about. So you can see that firstly, the output of your approximated the output of your approximation and the output of the original function, they are the same at this point. Next thing is the instantaneous rate of change of the approximated function and the original function are the same. You can see that the slope field are the same. Okay, they increase with the same amount. It's quite similar. And the concavities of your approximated function and your original function is the same. I mean, concavity means open up or open down. Okay, so over here you see that the green curve. I mean, the original function is the green curve, and around this point it is open up, right? This is open up, and for your approximated integral, I'm sorry, for the approximated function, this is the red curve over here. I mean, because this should be the parabola, because this is the function. This is the function of order 2. So it should be a parabola. And the point is, around this point, your approximation also opens up like the way the green curve opened up. You see that? Okay, over here they open up. This one is also open up. So for the second order approximation, it will carry more information about your original function. Okay. So in general, if you want to, again, I mean, if you have more terms, in your approximation, you will have the better fit to your original function. So let me consider the general definitions of the Taylor polynomial. So let me denote T sub nx as the nth degree Taylor polynomial for the function f of x as the points x equal to a. So because this is n degree polynomial, so you're gonna have the highest power that you have for the polynomial will be n. Okay, the highest power for n. So you're gonna have a1 x to the power of 1 minus a2 x minus a squared, and you have you add more terms until you reach into the index n in the power. Okay, this is the n degree polynomial. So the last term should be x minus a to the n with the corresponding coefficient an. And the thing is, your approximation will carry the informations of your original function. Okay, the polynomial approximation will carry the information of your original function, in the sense that it will carry the informations of all of the derivative. So firstly, the output of your approximated polynomial will be the same as the output of your original function. The first derivative equal to the first derivative of your original function. The concavities of your polynomial will be the same as the concavities of your original function, and keep moving on. You're gonna have that the function and the first and the derivatives will agree at x equal to a. Okay, so it will carry a lot of information in terms of output, in terms of derivative of your original function at the point a. Okay, so that is the 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 ideas about the the function approximations, and we're gonna use polynomial to approximate the function. Okay, so remember that the more term you have, the better its approximation is, and the Taylor polynomial will have a responsibility to carry the information of the original function in terms of output, in terms of rate of change, in terms of concavity, and more information about derivative. Okay, so this is the key thing. Remember that your Taylor polynomial approximation will carry the information about the derivative of your original function. So over here, let me suppose that I have the function f of x equal to psi of x. So if I use the 0-degree polynomial, then my function, my approximation is just zero. I mean, this one is not a good approximation because you don't use any terms. But if you use the T1, if you use T1 of x, then you write down the if you write down the Taylor polynomial expansion, you're gonna have x as the approximation. So this one is just a linear. This one is just a linear approximation. So it may do a good job for the points for the point that in the neighborhood of 0, 0. But if you move further and further, like I mean over here, the red curve that I have is the psi of x, and the blue line that that I have a y equal to x. Okay, so this is the I would say this one is the uh, the tangent line. Okay, the blue line is the tangent line for the function psi of x at the point x equal to 0. Okay, the point is it they look, I mean, they looks good in the neighborhood of 0. Okay, but it does not carry much information about the original function. It doesn't carry any kind of concavity information. So that means you have to use more terms. You have to use more terms in your approximation to kind of capture the concavity, the informations about the original function derivatives. Okay. So for instance, over here, I use the order three Taylor polynomial. Okay, the grid three Taylor polynomial, and this is this one is the green curve. So over here, when I craft the green curve, okay, you can see that around in the neighborhood of the point 0, 0, you can see that the green curve do a pretty good job in approximating the function psi of x. You can see that firstly, the output of your polynomial and the output of the original function psi of x, they agree at the point 0. They also have the same rate of change. You can see that they kind of increasing in the neighborhood of 0 as well. And more than that, the function, the your approximated function also have have the same concavity compared to your original function. You can see that over here, your original function kind of opens up. Your approximated function also kind of opens up. Over here, your original function kind of open down, and your approximated function on kind of opens down as well. And if you move to a nor if you want to use more terms, over here I use the Taylor polynomial of degree 5. Okay, so when I wrote down this thing and I crafted this function, the purple curve over here is my approximated function. Okay, and now it kind of carrying more information. You can see that over here your function kind of open down, your approximated function also kind of open down. Over here it opens up, your function also opens up, and for the concavities over here, they are completely the same. So again, you can see that when you move from the first degree Taylor polynomial into the fifth degree Taylor polynomial, your approximation function becomes better and better. It from the line, it does not contain any concavity information. When you move from the line to the approximation by the ring curve, Now you have some concavities in your approximated function, and if you move to the fifth degree polynomial, you're gonna have the better concavity information about your original function as well. So that is how the function approximation look like, and the question is how can we establish the Taylor polynomial over here? I just list out the Taylor polynomial for the function psi of x, but I didn't tell you how can we write down x minus x cubed divided by 6. How can we write down x minus x cubed divided by 6 plus x to the power of 5 over 120. Okay, where this thing coming from? So this is the question: how can we establish the Taylor polynomial? Okay, so again, I want to emphasize that the nth degree we're gonna set up things in a general way. So I will consider the nth degree Taylor polynomial for the function f at the points x equal to a. Okay, so I'm gonna write down the polynomial, which is the approximation function to the original function at the points x equal to a. Okay, at the point x equal to a. So you're gonna have x minus a, x minus a, x minus a, x minus a as the main core. Okay, over here, because you want to write down the approximation at x equal to a. So remember that x minus a is the main core. Okay, the main things of your function approximation. And because I'm gonna use the nth degree polynomial, so I will write down a0 x minus a to the power of 1 with the coefficient a1, x minus a to the power of 2 with coefficient a2, and I keep writing them down until I have x minus a to the power of n with the coefficient an. Remember that I should have x minus a to the power of n because I'm using the nth degree polynomial. And the important thing is your approximation polynomial should carry the information in terms of derivative of your original function. Okay, again, your Taylor polynomial approximation should carry the informations of your original function in terms of derivative. Okay, so you have to make sure your approximation satisfy these conditions. Okay, so for instance, let me consider the simple case. Let's write down the second order approximations for the function f of x. So I'm going to find t sub 2x, okay, the second order approximation for my original function. So let's say if I want to write down t2x, that means my approximations will be the polynomial of degree 2. Okay, so I will have a0, I will have a1, x minus a, I will have a2, x minus a to the power of 2, and that's it, because I just want to use the degree 2 polynomial. So this one is good enough, and I stop here. I mean, you can add more terms, but the question is, we just want to write out the second order approximation. So I just stop when I have x minus a to the power of 2. Okay, so over here, remember that your approximation should carry the informations of your original function in terms of derivative. So I'm going to find out the formulation for my T2 prime and T2 double prime. Okay, so T2 prime will be derivative of A0 is 0, derivative, because A0 is just a number, so when you take derivative, it becomes 0. Derivative of x minus a is 1. Okay, when you take derivative of x minus a, you're going to have 1 minus 0, and you still have a1 in the front, so you have a1. What is the derivative of this thing? So you bring 2 into the front, you have 2a2 times x minus a. Okay, and if you take one more derivative, a1 vanish, x minus a vanish. Not vanish in the sense of 0. When you take derivative of x minus a, you take derivative, you're going to have 0. I'm sorry, the x minus a prime, you're gonna have 1. Okay, so that means you have 2a2 times 1, so you have 2a2. Okay, so from here, remember that you need your polynomial approximation should carry the information over here. So I need to figure out what is the output for T1, TNA, Tn primes of A, T, the n degree derivative of T as well. Okay, so from here, this is the function for T2x. So if I plug in the input A, okay, I'm gonna have A0, because if you plug in A, this thing vanished. A minus A0, A minus A0. For the slope field of the approximation, I'm gonna plug in A to my formulation. So if I plug in A, I'm gonna have A1, okay? And if I plug in A into my second order derivative, I'm gonna have 2A2. Okay, so from here, because we want the approximation carry the information of your original function in terms of the output of the function and derivative. That means from here you have that a of 0 is f of a. Okay, you see that a of 0 should be f of a. For T2 primes of A, T2 primes of A is A1. So you have A1 equal to F primes of A. And for T2 double primes of A, we have 2A2. So 2A2 equal to F double primes of A. So from here, you have that A0 will be determined by F of A. A1 will be F primes of A, and A2 going to be F double primes of A divided by 2. Okay, so over here, the question wants us to find T2 of X. Okay, the question wants us to find T2 of X. Then, and it turns out that you need to write down the formulation for the degree 2 polynomial, okay, in this form. Okay, so over here, if you want to complete your approximation, you need to figure out the numbers for A0, A1, and A2, the coefficient. You need to find the coefficient. And these three coefficients will be given by f of A, f primes of A, and f double primes of A divided by 2. A0 is f of A, A1 will be f primes of A, and A2 will be f double primes of A divided by 2. Okay, that is how you find out the coefficient for your polynomial approximations. Okay, in the next videos, I'm gonna talk about how can we find out the fourth degree polynomial as the approximation.